Hey guys, this is the fourth of our 9 common techniques for rewriting integrands so that our basic antidifferentiation rules apply. And the fourth technique is long division. I'm only going to use this when the integrand is a rational function, and just remember, rational function just means a polynomial divided by a polynomial. So you've got some polynomial up here, and you're dividing by some polynomial down here. We're also going to learn another technique later for dealing with these problems, but the ones that are in your homework for this first section only require long division and the techniques that we've covered so far in this class. But if you've got a polynomial over a polynomial and your basic rules do not apply and it's not a u-substitution, you want to try long division. And generally, we're going to use long division whenever the degree of the numerator is greater than the degree of the denominator. Now remember what degree means. Degree, the degree of a polynomial is, in this case, if it's a polynomial in one variable, it's the highest power of x in that polynomial. So that's an x cubed, so this is degree 3. And that's an x squared, so that's degree 2. So the degree of the numerator is greater than the degree of the denominator here. So this is a good candidate for long division. Now, we can use this technique whenever the degree of the numerator is also equal to the degree of the denominator, but there's an easier technique in that case called adding a well-chosen zero. We're going to do that a little bit later. For right now, we're just going to stick to this rule. If it's a rational function and the degree of the numerator is greater than the degree of the denominator and basic rules do not apply and u-substitution does not apply, we're going to use long division. So first we should check it out. Do our basic rules apply? No. Look at this. Do we have anything on our list that looks even remotely like that? Well, you know, the 1 over this, I've got something for that. Like that looks like an arctangent function from my list. But what am I going to do about this x cubed, this 3x cubed and the 55x? That's not going to work. So I don't have a basic rule for that. U-substitution would also be an option, but with U-substitution, if you're dealing with a rational function or a quotient involving functions, if there are no radicals, there are no exponents, there are no trig functions, there's nothing, if there's nothing to nest inside of another function, well, usually the only choice for you is the denominator in that case. Or maybe you can add some fancy parentheses or something somewhere, some like hidden parentheses, and use a u-sub, but I mean, I'm not seeing that here. If I let u be this, the derivative is a 2x, and I could handle that 55x, but what about the 1? What about the 3x cubed? So u-sub doesn't apply. So we checked. Basic rules do not apply. Oops, basic rules don't apply. U-sub does not apply. So we're going to go straight for long division. So let's do the long division. Now whenever you're dividing polynomials, the one in the denominator is called the divisor. And that goes out here. And then you've got this little division box, the one in the numerator. It's called the dividend. And then your quotient goes up here. And we're going to do a bunch of work. I'm going to follow the division algorithm. Eventually we're going to have a remainder down here. We'll talk about when to stop. We'll talk about when we've got our remainder. And it turns out that after we've done all of this, the dividend, that was the original numerator, divided by the divisor, is always equal to the quotient plus the remainder over the divisor. Now we can elaborate on this just by talking about arithmetic. Let's say you've got 275 and you want to divide that by 13. Well, using the division algorithm, 13 goes outside, 275 goes inside, right? And I ask myself, well, how many times does 13 go into 2? Well, it doesn't. So how many times does 13 go into 27? It goes into it twice. So we put that number there, and then we multiply these two guys, and we get a 26. And then we subtract, bring the 1 down, bring the 5 down, and then we start again. That's very similar to what we're going to do here. Then once we've started again, we say, how many times does 13 go into 15? Goes in once. Then you do the 13 just times the 1. 13 times the 1 is 13. Subtract, and you get a 2. Now, if we're not looking for repeating decimals, we're not trying to get a decimal approximation, this is the quotient. And this is our remainder. So according to this formula up here, 13, or 275 divided by 13 is 21, plus 2 out of 13. And I think that makes sense. That's telling us that 13 goes into 275 21 times, and then there are just two extra left over. And if you want to check to be sure, you should multiply 13 times 21 and then add 2, and hopefully you'll get 275. That's how we can check. We're going to do the same thing over here with our polynomials. It's a little long, but it's okay, we can handle it. Now, one thing that you should keep in mind here when dividing polynomials is that it's especially important under this division bar that we include all of the powers of x here, starting with the highest power of x in our numerator. So we're going to start with 3x cubed, and then I want an x squared term, an x term, and a constant term. Like I want all the powers of x starting at x cubed and going all the way down to x to the 0. So next I would add an x squared, but there is no x squared term, so I'm going to have a 0x squared as a placeholder. Then I'll add my x term, that's the 55, 55x, and then I add my constant term, which is the -1. Okay. Now, over here I asked myself, how many times does 13 go into 27? And I said 2 times. And I wrote that up here, and then I multiplied. This is very similar, but we're not going to look at the whole thing. We're just going to look at the leading term of this and the leading term of that. And we're going to ask ourselves, how many times does x squared go into 3x cubed? Or alternatively, x squared times what will give me a 3x cubed? Well, I need a 3. I've got 2 x's, I need 1 more x. So x squared times 3x gives me that 3x cubed. So I'm going to write 3x up here, and I just like to organize it this way. If that's got an x to the first, I'm going to write my 3x over the other x to the first term right here. And then I'm going to multiply. Just like we did the 2 times the 13 equals the 26, we're going to take 3x and we're going to multiply it by this, and we're going to write our product down here. Now, this is a little different though, because this has 2 terms, and we're multiplying a monomial by a binomial. So that means we've got to distribute. You've got to do the 3x times the x squared and the 3x times the 16. So 3x times x squared is 3x cubed, and 3x times 16 is 48x. Now at this point in our algorithm, we subtract. Now remember, whenever you're subtracting polynomials, you usually have a negative outside some parentheses. Then you distribute that negative through the parentheses, and then you collect like terms. That's the same as just changing all of these signs and then adding like terms in the columns. So that's what we're going to do. So change the signs and add 3x cubed to minus 3x cubed, 0x cubed, those i's are gone. 55x minus 48x is 7x. Bring down the -1. And then ask yourself, how many times does x squared go into 7x? You might say it doesn't. Like, yes and no. Another way to think about it is x squared times what will give you 7x? The only way that will happen is if I have an x or 7 divided by x, so that one of those x's would cancel. And I don't want division up here. anywhere. So that tells me this is my remainder. Another way that you can know to stop the division algorithm is to look at the degree of this, this expression right here. It's not exactly a remainder yet, but it's sort of an intermediate remainder. If the degree of this is less than the degree of this, then you can stop. That's the actual remainder. This is degree 1, that's degree 2. So this is our remainder. This guy is our quotient. And that means our original integrand is equal to 3x plus, that's our quotient, plus the remainder, 7x minus 1, over the divisor, which is x squared plus 16. Remember, this guy is your divisor, the original denominator. All right, I've got a rule for that. Do I have a rule for that? Say, well, no, not technically. But if I got rid of the negative 1, I'd have a u-sub. And if I got rid of the 7x, I'd have an arctan. So I can separate the numerator on this one. It's a good practice of separating the numerator as well. So we're going to separate the numerator on the second one. 7x over x squared plus 16 minus 1 over x squared plus 16. Use your power rule here. Bring the 3 down. Add 1 to the exponent. Divide by the new exponent. There's going to be a plus c that comes from these last two guys. Do that separately. Here we're going to do a u-sub. U is the denominator. I know that you could let u equal x squared, but then you'd have u plus 16 down there. And it would be even nicer if that was just a u. The derivative of 16 is just 0, so it's not really going to change much. So if there is a constant in the denominator and you're using your denominator to be u, make sure you include that constant. It's going to make the calculation simpler. It's also going to allow you to avoid doing a u-sub again, like a double u-sub. You don't want to have to do that. So we've got u equals x squared plus 16. Take the derivative. Now I've got a 7x dx. Now I could think about exactly what constant I would have to multiply by to make this a 7x dx. I'm not going to do it. I'm just going to get x dx by itself. 1/2 of du turns out to be x dx. So I'm dividing both sides of this equation by 2. Dividing is the same as multiplying by 1/2. And then this guy, this integral, is going to become factor that out, and the x dx is 1/2 du. And I've still got a u in the denominator. That's my u. And the 7 is accounted for. The x dx is the 1/2 du, that's accounted for. So that's an implied 1 right there. And I've got a rule for that. That's a natural log. So we've got 3 over 2 times x squared plus 7 over 2 times the natural log of the absolute value of u plus whatever we get over here. Running out of space. Let's finish up our u-sub on the next page. I've got 3 over 2 x squared plus 7 over 2 natural log of the absolute value of u. But u was x squared plus 16, so we can substitute that in. And then the last thing we do is our last piece over here. Now that looks like our arctan rule. The arctan rule involved a 1 over x squared plus a squared, or a squared plus x squared. A is the constant part, or a squared is the constant part. So a squared is 16. Take the square root to get a by itself, so a is 4. And then according to our rules, we're going to have -1, bring that -1 out as a constant, times 1 over a arctan of x over a plus c, and a is 4. So we have a negative 1/4 arctan of x over 4 plus c. And I'm going to bring that down. I don't need the minus or the plus. I want a minus arctan of x over 4 plus c. And we could stop here. This is acceptable for a test or a quiz. Totally fine with me. But if you're checking your answer in the back of the book, they might have it written a little differently. And it's not because the absolute value bars aren't important. X squared plus 16 is always positive. X squared is always positive except for when it's 0, right? And then we add 16 to it, and then it's definitely positive. So this is a positive number. I don't need any absolute value bars if that's a positive number. So I've got 3 over 2x squared plus 7 over 2 natural log of x squared plus 16. Don't need the absolute value. It's okay if you put them there though. I'd rather that you put them there, you're especially conservative, than leave them off when what's inside the natural log might be negative, because then we'd have problems. Alright, and that's our antiderivative. Say, okay, well what was this video about again? We had a lot of work to do at the end, and we had to review a couple of techniques. But remember, this was about long division. That's right. If the degree of the numerator is greater than the degree of the denominator, you can do a little long division first. When you do, after the long division, your integrand can be rewritten in this way. Once you've written it in this way, all you have to do is a basic rule here, split this into 2 terms and do a u sub here, and then for the last term you do the arctangent rule. Okay, so that's long division. Here is just one more example of long division. Now in this one, because the degree of the denominator is 1, you could also use synthetic division. Synthetic division would be just fine and be a very efficient way of dividing this polynomial by this polynomial. So I'm going to do it both ways. I'm going to use long division again so that you can get practice with that algorithm. We'll need to use that algorithm if this is degree 2 or higher. Or at least if it's degree 2 and it's an irreducible quadratic. But if it's degree 1, you could get away with using synthetic division. That'd be a nice shortcut. But we're going to practice the algorithm one more time, and then I'll show you the shortcut. So, got the x minus 2, that's my divisor, goes outside. And then under this division bar, I'll have x to the 4th, and I want all of the powers of x starting with the 4th power. The next thing I need is a cubic term. So I've got negative 3x cubed. The one after that is an x squared term. So we'll have a 0x squared, because there's no x squared term up there. The next term after that should be an x term. That's 0x. And then the last thing should be a positive 2. Alright, so then I ask myself, looking at this guy and this guy, x times what gives me x to the 4th? X cubed. If you're not sure, you can always do this on the side. X times what gives me x to the 4th? The answer is x cubed. So I'm going to write my x cubed right here. Then we multiply. I've got these two guys times the x cubed. So you want to distribute. X cubed times x is x to the 4th. X cubed times negative 2 is negative 2x cubed. And then we're subtracting. And remember, when you subtract a polynomial, you just change the signs on the second one and then you add like terms. So we're just going to change the signs and add. X to the fourth minus x to the fourth is 0, x to the fourth. That's good. Those should always cancel if you chose the right thing up here. And then we've got negative 3x cubed plus 2x cubed is negative 1x cubed. Bring down the 0x squared and start again. Say x times what is going to give me a negative x cubed. Well, for the coefficient I know I need a negative. I've got 1x, I need 3, so I need 2 more. So I've got a negative x squared. I'm going to put that above the x squared term here, and then multiply. Negative x squared times x is negative x cubed. Negative x squared times negative 2. Negative times a negative is positive. We do that. Then change the signs and add like terms and columns. Negative x cubed plus x cubed is 0x cubed. Those guys are gone. And then we've got minus 2x squared right there. 0 minus 2 is negative 2. Bring the 0x down. Start over. X times what will give me the negative 2x squared. I need a negative 2 and an x. So it's going to go right there. Now distribute. Negative 2x times x is a, oops, I'm going to use pink. Negative 2x squared. Negative 2x times negative 2 is positive 4x. We're subtracting, so change the signs and add in columns. Add like terms. Negative 2x squared plus 2x squared is 0x squared by design, that's good. And 0 minus 4x is negative 4x. Bring the 2 down. Notice this is degree 1 and this is degree 1, so we can keep going. The degrees are the same. So I ask myself, x times what gives me negative 4x? I'm just missing the negative 4. So that negative 4 goes there, and then we distribute. Negative 4 times x is negative 4x. Negative 4 times negative 2 is positive 8. We're subtracting polynomials, so we change the signs and add. Negative 4x plus 4x is 0x, and 2 minus 8 is negative 6. This is degree 0, has no x's in it. That's degree 1, has 1 x in it, x to the first, so that must be our remainder. And this up here is our quotient. And don't forget, this guy is the divisor. So we get, after dividing this by this, we get the quotient plus the remainder, or minus the 6, over the divisor. It's always quotient plus remainder over divisor. Alright, and there's actually an easier way. You might be begging for an easier way. I'll show you how to do that, but it really only works when the denominator is a first degree polynomial in x. Or a different variable, but if it's a first degree polynomial, we can use synthetic division. So this is good practice for us in those cases when it's not a first degree polynomial. Okay, so now we're ready to apply our rules. These 4 guys all have rules, and that one's going to require a simple u-sub. So in this one, I want to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Bring your negative 2 down. Add 1 to the exponent, divide by the new exponent. The antiderivative of a constant is the constant times your variable of integration. And here, I'm going to factor out the negative 6 and think of that as a 1 over x minus 2 dx. Again, if you don't believe me, if you're not sure that that's algebraically equivalent, write that as a negative 6 over 1, multiply straight across. You get that back. So you know now, if you multiply those two fractions together, you get that. So these two guys, this and this, are equivalent to each other. All right, so to do this last one, I need a u-sub. I don't have a rule for 1 over x minus 2, but I do have a rule for 1 over x. So I'm going to let u be x minus 2. And because u is so simple, du is just 1 times dx. So this is du, this is 1 over u, and so we end up with a negative 6 times the integral of 1 over u du. 1 over u times du. Remember, that 1 is still there. And we've got a rule for that. That's a log. I'm going to bring everything else down. I like to keep things equal. If I say it's going to be equal, I want it to be equal. So I've got that. Now we're ready to antidifferentiate. The antiderivative of 1 over u is natural log of the absolute value of u plus c. And then don't forget to back substitute. We need a final answer in terms of x, not u. U is something we made up so that we could antidifferentiate. So replace the u with the x minus 2. And that's it, you're done. Okay, for those of you that want the shortcut that only works when this is a first degree polynomial, here is your long division shortcut in that case. This is called synthetic division. It's a quicker way to get this rewritten integrand. Okay, so the first thing you need to do is I'm going to write p of x over d of x. P is the polynomial in the numerator, d of x is the polynomial in the denominator. And you need to write p with all the powers of x, including missing powers, starting with the highest power of x that's already there. So I've got an x to the 4th. And I need an x cubed term, and I have one, so I'll write that down. And I need an x squared term. I don't have one, so I need to write a 0x squared in. I need an x term. I don't have one, so I add a 0x in. And then the constant term is a 2, so we're good there. And we would do the same thing with the divisor, but there are no missing powers of x. That's an x to the 1st. So I'm just going to write x minus 2 there. Now to do synthetic division, the first thing you do is you set the divisor equal to 0 and solve for x. So I have x minus 2 equals 0, so x equals 2. That number goes in this little box over here. And then the coefficients of p of x go here. So those are the numbers in front of all of these powers of x. There is an implied 1 in front of that x to the 4th. Don't forget that. So you've got a 1, a negative 3, a 0, and a 2. And you can see why those zeros are very important. It's going to change your outcome tremendously if you forget to put in those placeholders. I'm going to draw a bar here. And then this is the way it works. I'm just showing you how to do this synthetic division algorithm. I'm not showing you why it works or where it comes from. It's actually really interesting. You might want to look that up in an old pre-calculus textbook if you have one. But this is just a quick little algorithm that will allow you to get the results of the division, the remainder plus the quotient plus the remainder over the divisor. So you set the divisor equal to 0, put that number in the box. Put the coefficients of the numerator over here. Bring the first coefficient down. Then multiply. 2 times 1, that's 2. Write that product right there. And then add. Negative 3 plus 2 is 1. Then multiply. 2 times 1 is 2, and then add. You get 2. Multiply, 4, add. You get a 4. Multiply, 6. Whoops, I did it wrong. Multiply, 8, excuse me. And then add. You get a 10. Ruh-roh, did I do something wrong? Oh, I did do something wrong. Do you guys see my mistake? I said multiply and add. That should be a negative. Okay. Multiply, add. Multiply, add. Multiply. There we go. Add. I'm sorry, guys. That wasn't a very good example. 2 minus 8 is negative 6. Okay, so this number at the end, that's your remainder. I get a remainder of negative 6, and notice that's the same remainder I got over here. So I know I've done it right. Now, this started as a 4th degree polynomial. When I divide out a 1st degree polynomial, the degree goes down by 1. So if it started off as 4th degree, when I divide out the x minus 2, the next or the power of x that's right here is going to be an x cubed. This is the degree goes down by 1. So this is the coefficient of x cubed, and that's the coefficient of x squared, the coefficient of x, and then the constant, and then your remainder goes over your divisor. Okay, I'm sorry about the sign error that I made earlier. I'm glad we fixed it, but you can see we got exactly the same integrand that we would have gotten using the division algorithm. Once you do that, then you just do this. So that's long division, guys.